I am standing on the Harvard Bridge in Boston, Massachusetts, United States. Well, in the video I am. I'm recording the audio in post because I don't want to talk into the wind. This bridge is famous for its length being measured in smoots. A smoot was the height of Oliver Smoot, a student at MIT in 1958, who lay himself across the bridge over and over to measure its length. I said in the previous cursed units video that I wouldn't talk about joke units like smoots, but I just happened to be in Boston, so I might as well take the opportunity while I'm on the other side of the globe. According to the markings, the whole bridge is 364.4 smoots, plus or minus an ear. Apparently the E in ear was originally spelt as an epsilon, like an error term, although it looks like that detail has disappeared in refurbishments. Now, if you ask me, I would have expected a much larger measurement uncertainty than one ear, but maybe Mr. Smoot had especially large ears, I don't know. Though I'd rather not criticize Smoot for the quality of his work, because the entire endeavor was effectively a hazing ritual for his fraternity, Lambda Chi Alpha. Smoot was chosen for the task of measuring the Harvard Bridge because he was the shortest in the class and would have to lay down and get up the most. As someone living outside the US where we don't typically have college fraternities, this sounds like a cult. But here's the thing, the Smoot is not a cursed unit, at least not in my opinion. It was designed for a single purpose with an appropriate level of precision and has remained pretty much unchanged ever since. It's just a length, it doesn't have much physical complexity or significance, and it hasn't been used in any absurd or inappropriate ways either, with the exception of the hazing ritual, of course. The Smoot hasn't existed for long enough to do anything cursed. No, the real cursed units of length are the ones that have history behind them, the ones that have been repeatedly revised and replaced until they are just a simulacrum of their original design. The real cursed units are the ones we don't question because they're so common, the ones we take for granted. The real cursed units of length are the foot and the mile, because for some reason a mile is exactly 5,280 feet. Now, it wasn't always this way. The mile used to be a perfectly round 5,000 feet. So what went wrong? Why did humanity decide to change the ratio between two of the most commonly used units of length to a large multiple of 11? To understand where these units came from and how they got warped beyond recognition, we need to go all the way back to ancient Rome. In the Roman Empire, a pace, or passus, was the distance of 2 footsteps, and a foot was defined as a fifth of a pace. The roads of the Roman Empire were delineated with stone markers placed every 1,000 paces. These were engraved with the number of miles from a particular city, a mile being 1,000 paces. This is the origin of the word milestone, and the word mile derives from the Latin milla, meaning thousand. Wait a minute, if milla is 1,000, then where did the word million come from? What? Anyway, 1,000 paces in a mile, 5 feet in a pace, so 5,000 feet in a mile. Perfectly sensible, and this system spread across Europe thanks to the dominance of the Roman Empire. But then, around 1000 AD, a different standard emerged from the agricultural sector of England, which would also spread to the rest of Europe via the British Empire. An acre was a long stretch of land that's approximately the area a pair of oxen can plow in a day. An acre is 1 chain by 1 furlong, a furlong being 10 chains. A chain is 4 rods, and a rod is a long metal stick used for surveying land for tax purposes. Another perfectly sensible system, I think. So what went wrong? Well, the first thing that went wrong was someone measured the length of one of those metal rods in feet and got 16.5 feet. A nice round 33 divided by 2. And this became the standard definition of the rod in the English legal system somewhere around 1400 or 1500 AD. There seems to be disagreement on the history of why everyone suddenly found feet so important when the taxation system was previously using rods. The British Isles were invaded quite a lot during the Middle Ages, and every invader seemed to want to introduce their own units. But for some reason, despite the foot being formalized in a statute, the mile took another century or so to settle down. A mile stayed as a generally vague long unit until, during the reign of Queen Elizabeth I, it was pinned down to a value of 8 furlongs. Once again, there's not a lot of good data on why the mile was changed to this value in particular. One explanation is that the furlong was conflated with the Roman stadion, which was an eighth of a mile. I found an article claiming that Wycliffe's translation of the Christian Bible into English directly translates stadion into furlong, and perhaps this solidified the connection. Whatever the case, a mile is now 8 furlongs, a furlong is 10 chains, a chain is 4 rods, and a rod is 16.5 feet. So in total, 1 mile is 5,280 feet. Then that entire system got transported to America, where it got baked into United States law and bureaucracy, and then curled up and hid itself from the metric system emerging in Europe, and that's where we are today. So, in short, feet and miles are related in such a horrible way because they are each independently grafted onto another incompatible set of units that has mostly fallen out of usage. This brings me to what I think is the most cursed US customary unit, the acre-foot, a unit of volume still used today for water reservoir capacity. An acre-foot is about 1,200 cubic meters. It's a foot times a chain times a furlong, and it's a horrible merger of two systems that never should have been combined. Wait, why are we in a screen transition? Go back, I'm not done with imperial units. You see, the acre-foot is not the most common imperial unit of volume, not by a long shot. Probably the most common one is the gallon, which is used for volumes of liquids like water or fuel. But we have to be careful here, because there are two different systems of units we could be talking about, imperial units and US customary units, and they have different gallons. Imperial units are the ones used in the UK and a few other places, with the word imperial referring to the British Empire. US customary units are a separate system which Americans often incorrectly refer to as imperial units. They have some overlap, notably feet and miles. Well, almost, we'll get to that later. But there are some big differences as well. Both systems have a unit called the gallon, and the two gallons are not the same at all. The imperial gallon is about 1.2 times the US gallon. That's a pretty big difference. How did that happen? Well, prior to the 1800s, there were a lot of different types of gallon, usually used for measuring various alcohols. The modern imperial unit evolved from the ale gallon, while the modern US unit evolved from the wine gallon. Let's see how these came to be defined. The wine gallon is defined as 231 cubic inches. That's 3 times 7 times 11. Now, I searched far and wide and only found one vaguely convincing explanation for this number from a website which references a 1706 English statute. 231 cubic inches could be the volume of some standardized container, which might have been a cylinder with height 6 inches and diameter 7 inches. Well, almost. The volume of a cylinder involves a factor of pi, an irrational number. To get 231, you have to use the classic approximation pi equals 22/7. Fantastic. It's likely that the wine gallon existed before this definition, and the numbers 6 and 7 were chosen to match it for historical consistency, and not because they would become a meme in 2025. Or perhaps the whole standard wine cylinder thing is just grasping at straws. I have no idea. Anyway, let's see if the imperial gallon is any better. An ale gallon is the volume of 10 pounds of water. Well, that sounds very reasonable, except for one minor detail. The pound has absolutely no relation to any of the other units I've mentioned. It evolved from the Roman libra, from which we get the symbol lb, and I would have expected that the Roman libra was some object based on the foot, similarly to how we define the gram to be the mass of a cubic centimeter of water. But no, as far as I can tell, it's just some random weight. Which means imperial gallons do not have a nice ratio with cubic inches, not even one involving pi. The imperial gallon is about 277.4 cubic inches, and that number doesn't have any special historical origin. There's a bunch of other units of volume derived from gallons, but since the US and imperial gallons come from different units, these derivations are also different. For example, a fluid ounce is the volume of an ounce of water, an ounce being a 16th of a pound. This means that a fluid ounce is a 160th of an imperial gallon, but also a 128th of a US gallon, with these ratios originating from the ale and wine gallons I described earlier. So at least the fluid ounce is uniform between the two systems. But wait a minute, 128 times 1.2 is not 160, it's about 154. So the fluid ounce is not uniform. The US fluid ounce is about 4% bigger than the imperial fluid ounce. It's not 20% like the gallon, but I think 4% is still pretty substantial. So to recap, gallons are different in the US and the UK, so the ratio between gallons and fluid ounces in each system attempts to correct this. But the correction is wrong, so fluid ounces are still different between the two systems. Quarts and pints are defined in terms of the gallon using the same ratios in both systems, which means they are off by a factor of 1.2 as well. Meanwhile, cups, tablespoons, and teaspoons are all over the place. Conventionally, a tablespoon is half a fluid ounce, but then there's disagreement on how many teaspoons are in a tablespoon. Today, however, it seems like cookbook authors and utensils manufacturers have accepted that everything should just be in milliliters, aka cubic centimeters, and this has led to a new metricized system of volumes. Unfortunately, even after converting to metric, we're still inconsistent. A metric cup is often 250 milliliters, but the US legal cup used for food labels is 240. Fortunately, everyone seems to agree on the smaller metricized units. A teaspoon is exactly 5 milliliters, and a tablespoon is exactly 15 milliliters. Unless you are in Australia, where our tablespoon is 20 milliliters. This is a weird instance where Australia is somehow more British than the UK. The unit of 1 teaspoon originated from the British fluid dram, which was a quarter of a tablespoon, but teaspoons had experienced a sort of inflation in the 1800s, so the US ended up changing the ratio to a third instead of a quarter. And when everything got metricized, the rest of the world followed them. But not us. We stuck with the empire, because it's 4 teaspoons in a tablespoon, not 3. We derived the exact value of the teaspoon from the US system, but derived the teaspoon-tablespoon ratio from the imperial system. And just to prove that this is a real thing and I'm not talking bollocks, I took a trip to the supermarket. This is a 15 milliliter tablespoon, and this is a 20 milliliter tablespoon. Look, I'm sorry. We're really sorry. Australia is normally good with units. This is like the only weird one, I swear. No, I'm still not done. I need to go back to pounds for a second. In the first Cursed Units video, I explained how physical constants need to be translated between different units, and gave an example where I put the gravitational constant in feet and pounds. This apparently left a lot of viewers very confused, because they had been taught that the pound was a unit of force like the Newton, not a unit of mass like the kilogram. This was my mistake, but also everyone else's mistake, and also just the mistake of humanity in general, because it turns out that there is both a pound force and a pound mass. A pound force is the gravitational force exerted by an object with a mass of 1 pound mass on Earth. Historically, mass and weight were conflated with one another, which is why we have this confusion. But notice that the relation between the pound mass and pound force is not the same as the relation between mass and force units in the metric system. A newton is exactly 1 kilogram times a meter per second squared. In other words, a newton is the force required to accelerate a 1 kilogram object by 1 meter per second every second. The pound force, on the other hand, is the pound mass times the gravitational acceleration at the Earth's surface. This is only useful if the force you are describing is gravity, and specifically gravity on Earth. On the Moon, a pound mass weighs a lot less than a pound force. Now, around 1900, there were already derived units based on the pound force, things like the pound-foot for torque and pounds per square inch for pressure. So eventually various fields and industries came around to the idea that we shouldn't be using the pound mass anymore, and a new unit of mass was invented called the slug. A slug is the mass of an object which accelerates by 1 foot per second every second when you apply a force of 1 pound force to it. Since gravity at the Earth's surface is about 32 feet per second squared, a slug is about 32 times the pound mass. The consequence of all of this is a lot of YouTube commenters patiently explaining to me that in fact the pound mass does not exist and I should be using the slug instead. Now, the reason I made this mistake is because, as I have mentioned, I grew up in Australia where everything is metric. But that also means I have no touchstone on how common these units are. I've seen a lot of people argue that when you see the word pound, you should always assume that it's a force. I've also seen a lot of people remark that they have never seen the slug before or that it's barely ever used. So I actually have no idea how Americans measure mass. By the way, there's another mass unit derived from the pound force using the inch instead of the foot. It's called the slinch, along with a bunch of other ridiculous names. But confusingly, for a fixed force, mass has an inverse relationship with acceleration, so the slinch is 12 times bigger than the slug, not smaller. We can never reach the bottom of the abyss that is customary and historical units. We could talk about how miles are different from nautical miles, a 60th of a degree of the Earth's circumference from which the knot is derived. We could talk about the British thermal unit being the energy required to raise 1 pound of water by 1 degree Fahrenheit. But the heat capacity of water depends very slightly on temperature and pressure, so what conditions are we using to define the BTU? You could be 0.5% off. We could talk about how the calorie is actually 1,000 calories depending on who you're speaking to. We could talk about how we divide the day into 24 parts, then 60 again, and then thousands, and somehow this awful system is the only system that we all agree on across the globe. Just kidding, we don't agree. Add this computer file interview with Tom Scott to your watch later list. During the metric revolution, there was an attempt to introduce decimal time, but it didn't catch on. But that's not the worst failed decimalization. Did you know that there exist tape measures delineated in tenths of a foot? This was brought to my attention by Alexander the OK in his video on the horrific units of oil drilling, which he cites as a major reason for him leaving the industry. Add that to your watch later list as well. We could talk about how both of the words inch and ounce come from the Latin word uncia, meaning 12th, but an ounce is a 16th of a pound and not a 12th. Rob Words talks about this in his video on the etymology of different units. Add that to your watch later list. Hey, the word pound also refers to British currency, right? That's because it was the value of a pound of silver minted into 240 pennies or 20 shillings. Except now the shilling is deprecated and there's 100 pennies in a pound because the government got sick of all the ridiculous coinage and shifted to decimal. Did you know that Britain used to have a 2 shilling coin and also a 2.5 shilling coin? You should watch this old video by BritMonkey who talks about pre-decimal currency. I'm giving you a lot of homework, aren't I? A lot of British homework as well. I suppose this video has become pretty much exclusively about the British Empire. My point is, it is well understood that customary units suck. Miles, gallons, furlongs, and fathoms may have once represented real things, but now they are so abstracted and have transformed so much that they are effectively arbitrary. These units are not a product of science and mathematics, nor are they really a product of our biological proportions or perception. Rather, they are an emergent feature of the uncontrollable turbulence of human history. If you're a Brit, you might look at the US and say, aha, they keep using silly units, despite the fact that all your road signs are still in miles. And if you're an American, you might look at the UK and say, aha, this is all your fault, it was your empire that introduced all these silly units. But no, it's everyone's fault that we keep using them. We are all complicit in this. Why are we like this? Why do we cling so unquestioningly to such archaic units? In short, it's because standardization is just difficult. And to demonstrate the difficulties of standardization, in a case where standardization actually worked, I now want to talk about the meter. Which, by the way, is spelt like this, America. If you don't use it, then you shouldn't get to decide how it's spelt. The meter is not a cursed unit. In fact, I think the meter is the least cursed unit in existence, and the meter not being cursed is a foundational achievement of the field of metrology. But by examining how it came to be defined, we can learn a lot about why it's so complicated to get precise standards for units. It also has a rather strange property regarding gravity that I want to ramble about for a bit. If you've been bored in school and fiddled around with a calculator in class, you might have accidentally discovered that pi squared is about 9.8. This is approximately the gravitational acceleration at the Earth's surface in meters per second squared, as printed on every high school physics formula sheet around the world. And it's very close, only about 0.5% off. Mathematical coincidences like this happen all the time, but still you might suspect that there's something deeper going on here. You might have heard somewhere that the meter is 1/40 millionth of the Earth's circumference and think that g equals pi squared is a consequence of that. But unfortunately the maths doesn't work out. The gravitational constant and the Earth's mass pop up in your equations and never cancel. So g equals pi squared has to be a coincidence, right? Amazingly, this is not a coincidence. There is an older definition of the meter where this equation is exact. In the 1600s and 1700s, a popular standard unit of length was the length of a second's pendulum, a pendulum that swings once every second. This is because the swinging rate of a pendulum does not depend on the mass of the pendulum or the swinging height, mostly. It only depends on the length, and that makes it a very consistent timekeeper. The pendulum in a pendulum clock, for instance, gradually loses energy and swings lower and lower over time, but despite this it still swings at almost the same frequency, so the clock doesn't go out of time. If you go through the physics, it turns out that the half period of a pendulum is pi times the square root of the length divided by the gravitational acceleration. If we define 1 meter to be the length such that this half period is 1 second, then we can rearrange to find that the constant g is pi squared meters per second squared. Mystery solved! This definition of the meter is pretty good, because measuring out a meter only requires that you have some way of measuring time, which you can do with a sundial. This means that people on opposite sides of the world can calibrate their instruments without ever having to communicate with each other. There's no need to ship meter sticks around the world. But there's a couple of slightly cursed details to this definition. Firstly, the swinging rate of a pendulum depends on the strength of gravity, which varies across the Earth's surface. It's the pound force, pound mass problem all over again. Secondly, this equation for the period relies on an approximation which assumes that the angle the pendulum swings out is quite small. It's not too significant. If you stay within an angle of about 15 degrees, your meter measurement should be off by less than 1%. But that's still big enough to notice if you're doing super precise measurements. It's also kind of awkward on a theoretical level. The figure of pi times the square root of L over g is only as accurate as possible when the swinging angle of the pendulum is as small as possible. So the ideal theoretical meter is the length of a second's pendulum with a swinging angle of 0, which means it's not swinging at all. Because of this, at the end of the 1700s, the meter was standardized to a more precise value. It was now defined to be 1/40,000,000th of the Earth's circumference, specifically measured along a line of longitude through Paris. This specific distance was chosen because it happens to be coincidentally very close to the pendulum definition, which makes this a very old example of backwards compatibility. It might seem strange to replace the pendulum definition with something that most people could not feasibly measure on their own, but by this point in time it was now possible to ship meter sticks around the world, so the French Academy of Sciences decided to just do one big expedition to measure out this distance as precisely as possible, and then manufacture a standard meter-long metal bar which other institutions could copy. With the engineering of the early 1900s, it was possible to create and measure standard meter sticks to within a micrometer of error, a millionth of the full length. But this still wasn't enough. By the mid-1900s, physicists were probing even smaller length scales to investigate quantum mechanics, so the meter had to be redefined again. At one point, it was 1,650,763.73 wavelengths of krypton-86 radiation. Today, we have come full circle and defined it in terms of the second again, but now the meter is 1/299,792,458th of the distance light travels in a second in a vacuum, and a second is defined as 9,192,631,770 periods of cesium-133 radiation. Once again, actually realizing this length physically is absurdly difficult, but once you have one realization, it can easily be copied. And once again, these particular numbers have been chosen because of backwards compatibility. The meter of today is still within a micrometer of the standard meter stick from the 1900s, and still within a few millimeters of the original pendulum definition. This is the grand achievement of SI, the International System of Units, a traceable chain of calibrations linking every realization of a unit to its standard definition. Today, we take standardized measurement for granted. We don't have to worry about whether our rulers are calibrated correctly or whether someone on the other side of the globe has a different convention for how long 1 second is. And the reason for this is a lot of people fighting to make it that way. The scientific study of measurement is called metrology, and it's not a small area of study. The International System of Units is established and maintained by an enormous number of organizations. The standardization of SI is so successful that even customary units like the foot are now calibrated using metric standards. Sometimes we can't agree on how to do this. I said earlier that imperial and US customary units have the same foot, but technically there is a tiny difference. The international foot is defined to be 0.3048 meters, but the US survey foot, which has been used for mapping and land surveying, was defined so that 1 meter is 39.37 inches, which makes the survey foot approximately 0.3048006 meters. That's a difference of half a micrometer. NIST, the US National Institute of Standards and Technology, officially deprecated the survey foot in 2022, but many people still hold on to that extra micrometer. Every so often, I see an imperial unit apologist in the comments, claiming that feet and inches are easier to understand and that makes them superior. I don't agree with this. I think being familiar with a unit is just a sign that you've used it a lot. But the point is, it doesn't matter. Every time you measure something with a tape measure, or weigh something on a scale, or do really anything to do with measurement, you're probably using an instrument that was manufactured to metric standards and then converted to customary units. And this isn't because the metric system is superior. It's because there is an international infrastructure that ensures that all your rulers are the same, and it just so happens that this infrastructure is built around the metric system. All of the researchers who develop methods to standardize and calibrate units, all of the engineers who put those units into physical appliances, and all of the lawmakers who encode those units into public policy are the reason that we don't have to worry about being ripped off at the supermarket, or getting pharmaceuticals with the wrong dosage, or having spaceships accidentally crash into Mars. Actually, that's a lie. We still have to worry about our spaceships crashing into Mars, because that's what happened to the Mars Climate Orbiter. You see, NASA commissioned a piece of software from Lockheed Martin to correct the spaceship's trajectory after certain maneuvers, and they used pound force when NASA was expecting newtons. So the ship went off course and approached Mars at too steep an angle and burned up in the atmosphere. If only we could convince the rest of America to change to metric. But who am I kidding? That's never going to happen. An international standard decreed by a highly centralized and bureaucratic committee? That's way too socialist for them to handle. Unless I'm abducted by aliens, there will be more videos in the Cursed Units series. For a start, I'm only familiar with customary units from English-speaking countries, so there are probably billions of people across the world that grew up with whole systems of units that I'm completely unaware of. Also, Alexander's video on oilfield units demonstrates that there are entire industries that use their own esoteric standards of measurement as well. So if you know a cursed unit from your home nation or industry, then I'd love to hear about it. Put it in the comments and I might bring it up in a follow-up video. And it's not all customary units. I still need to talk about decibels, sheet resistance, electron volts, and all sorts of other fun things. So stay tuned for that.